Hello, my name is Jussi Enkovara. This is the third part of a gentle introduction to parallel programming with MPI. In this part, we'll have a look at collective communication operations, which allows us to really start doing something with MPI. In this part of the tutorial, I'll introduce a couple of the most basic collective operations. Please bear in mind that there are many operations and functionalities in MPI not addressed in this tutorial. In MPI, there is a vast set of routines referred to as collective communications. These carry out operations where all the processes within the MPI communicator are involved. For example, there are routines for distributing data from one task to all tasks, and gathering data from all processes into one process, and routines for performing computations with global data. In principle, you could write a fully functional parallel program using only the first 5 or 6 MPI commands introduced in the second part of the tutorial. The collective operations just make the code more compact, easier to interpret, and they usually offer better performance. We will begin with a set of functions I call one-to-all functions. Our first function is broadcast, MPI bcast, which replicates a set of data from one process to all other processes of a group. The call to MPI bcast must be made by all the processes, not just the one that has the data you want to send to the others. The arguments to MPI bcast are the send buffer, which is the data we wish to broadcast, which could be a variable or an array, for example. Then we have the count, which is the number of entries in the send buffer, then the data type of the data, then the rank of the sending process, and finally the communicator where the operation takes place. In Fortran, like all other MPI routines, this routine has an additional argument, the return value. Note that the sending process can be any of the processes in the communicator. After all processes have completed the call, the data of the send buffer is the same on all processes. Another example of one-to-all communication is MPI scatter, where data contiguous in memory will be distributed equally among the processes. This time, again, we have the send buffer, then the send count, that is how many elements will be sent to other processes. Note that some elements will be sent to the process who is sending. Then we need to specify the data type of the elements, and then we provide a buffer where the local chunk will be stored, together with its size and type. Finally, the sending process and the communicator we are operating on must be specified. In these examples, we had to assume that the size of data is exactly divisible by the number of processes. In real life, this is not always the case, but that will not be a problem since there are related functions for collective operations that are able to handle varying sized pieces of data. They are formed by putting v at the end of the name of each routine. For example, MPI scatter would be then MPI scatter v. They are not discussed here today, but refer to the MPI standard or other web resources for further information. Now we are going to look at the reverse process to one-to-all communication, not surprisingly referred to as all-to-one. Let us take an example of the opposite of scatter, which is MPI gather. Its arguments are basically the same as with MPI scatter, but with the roles reversed. The send buffer and arguments describing it refer now to the local piece of data. Another important example of all-to-one operation is the global computation operation MPI reduce. In it, some operation, let it be sum, product, minimum value search, or what have you, is performed on the distributed data, and the result is returned into one task. For example, a global sum would be computed by calling MPI reduce with the arguments as the local variable to be summed as the send buffer, then specifying the number of elements in the buffer, in this example 1 element, the data type of the buffer, then the operation, in our case it would be equal to MPI sum, then the rank where the result is stored, it will not be available in other ranks, and then the usual suspects, communicator, and the optional error code argument. Let's have another look at the last example, the global sum. With MPI reduce, the result was only returned to one process. What if we needed all the tasks to hold the result? Of course, we could simply use MPI pcast to send the result to all tasks. But we can also do this with a single function, MPI all reduce, a function which represents an example of all-to-all communication. The procedure is very similar to MPI reduce, only that there is no root rank specified, so the result will be available for all tasks after the call has completed. A further operation which is of particular importance is MPI all gather. This is basically an MPI gather followed by an MPI pcast. Again, the argument listing is the same as for MPI gather without the root process. Other commonly used all-to-all routines include MPI all-to-all, which represents a sort of an all scatter, as well as the varying sized versions of some routines, for example MPI all-to-all V. Finally, I would like to point out two common mistakes with collective operations. First, all the processes must call the same function. It won't complete until every process in the communicator has completed it. So, don't put a collective operation in an if branch if there is a chance that all tasks won't make it to the call side. Second, don't use the same variable or array as both an input and output argument, for example, as send and receive buffer in the same call. To summarize this last part of the tutorial, collective operations in MPI are functions that distribute or gather data or perform collective computations. They make your program easy to read and almost certainly faster to execute. We discussed some of these operations, giving basic examples of one-to-all, all-to-one, and all-to-all operations. But there are more available. This part concludes now our fast tutorial to the very basics of MPI. I hope you understood and enjoyed the message I broadcast.